there guys, so tackling gradients in analytical geometry. I know as much as you all probably love functions, you don't really escape it in paper 2 with analytical geometry because we'll still focus on straight line functions sometimes when we work on a Cartesian plane, right? So I'm going to chat about straight line functions briefly, right? It's easy like how to determine the equation given whatever information you have, but also more importantly, the different ways that we can determine our gradient, right? Because from a grade 10 knowledge, we know there's 3 ways, and in grade 11, you learn an additional way that involves gradients as well. So I'll first touch on these 3 ways, okay? We know straight lines have the function y is equal to mx plus c, right? Or ax plus q, depending on whatever your teacher taught, right? We will always find m first, right? And m is my gradient. Okay, so the 3 ways that we can determine my gradient. Gradient obviously also just being the slope of the line, right? How steep a line is. We know then that if gradients go that way, we're dealing with positive gradients. We also then know that if gradients are going that way, we're dealing with negative gradients. Sorry, I don't know why I started to talk like that. It started to sound like ASMR or something. Right, so gradient, slope. First way is the traditional way that we've all familiar with, gradient formula. So we know that given 2 coordinates on a line segment, we'll be able to find the gradient of that line. All we'll do is we'll say that the change in y over the change in x will give me my gradient. What that means is that if I have a line and let's say this coordinate is a, -3 and 6, and that's b, also on the same line, and that is, what am I saying, 2 and -4, let's hope that works out, and I want to know what is the gradient of line AB. I will say small m of AB, right? Always just let them know one line you're working with is equal to change in y over change in x, right? Notice they're the same thing, and then I'll say 2b will be my point 2, so I'll say -4 -6 all over 2 -3. So very important here, make sure that your coordinates they sort of lie on top of each other, the actual coordinates. So we'll see 2 and -4 and -3 and 6. Right, very important you get it in the right order. So if this is going to be your coordinate 2, which it was for me, then that is x2 and y2. If this is going to be coordinate 1, then that is x1 and y1. Right, very important. So then we substitute it in. Notice that when I sub in negatives, again I pop in my brackets because it's minus that coordinate, which is -3. Right, that will become -10 all over +5, worked out perfectly. -2 is my gradient, which makes sense because we know negative lines go that way. That's just another way to check if I'm on the right track. So gradient formula is my first way. Okay, let's just erase the board. So the second way that we can determine gradients, well, I'll do the second and third way together. Okay, so the second way is given parallel lines, or at least given the knowledge that we're dealing with parallel lines, and my third way would be given perpendicular lines. Right, so firstly, parallel lines. We know parallel lines are anytime lines run in the same direction with the same distance between them at any point on those lines, right? Those lines will never ever meet. So parallel lines, obviously the symbol for parallel, going that way, and usually they'll have arrows denoting that they are parallel. So that is line AB is parallel to line CD. Okay, so when we know we're dealing with parallel lines, I know that the gradients of parallel lines are the same. Okay, parallel lines will have the same gradient. So if AB has an equation y equal to 2x plus 4, then without even knowing much about CD, I know it will also be 2x. Right, you see the same gradient. Very important here though is that the lines do not have the same equation. So you cannot say that the equation of line CD is also 2x plus 4, because it might have a different C value. It will have a different C value, because if it has the same C value, then it is line AB. So keep in mind that only the gradients are the same, not the C values, or also known as the y-intercepts. Y-intercept. Right, because the C value is the y-intercept of straight lines. Okay, so parallel lines have the same gradients. Perpendicular lines, right, symbol for perpendicular, the gradients will be inverses of each other. Meaning, also perpendicular lines are lines that meet at 90 degrees, symbol for perpendicular. Line AB and CD are perpendicular. That would mean that when I multiply or find the product of the gradient of AB and of CD, I will always get -1. So easy way to do this, I always say, is to flip the fraction and change the sign. Okay, so what does that mean? That means that if I'm given the gradient of AB is equal to a half, okay, right, positive. If I know they are perpendicular, the gradient of CD will be flip the fraction. So if I flip 1 over 2, it will become 2 over 1, which is just 2. That is positive. I'll change the sign. So CD must be negative. Just be sure to indicate that you know this is then your reason for that. Okay. Do another example quickly. If I say the gradient of AB is 4, and I want to know what is the gradient of CD, let's say it's -4. What is 4 as a fraction? 4 as a fraction is 4 over 1. So if I flip it, it will become a quarter. Change the sign from negative to positive, and that is perpendicular lines. Okay, so we can find our gradients using any one of those 3 ways. Gradient formula, having knowledge of parallel lines, having knowledge of perpendicular lines, and that's how we'll find M. In order to find C, if we're not given our y-intercept, all we'll do is we'll sub in coordinates for x and y. Very important, whenever we sub in coordinates to find C, they need to be coordinates that lie on the line. Otherwise, we're not finding C for that line. Plug in your coordinates, solve for C, and that's how you'll find the equation of a line. Okay, stay tuned for our next video, where we'll then touch on your actual grade 11 work in analytical geometry.